Good morning. In today's class, we will be studying another version of Huffman coding. In the previous lecture, we have seen what Huffman coding means. It falls under greedy approach. It falls under greedy approach, and this algorithm is used for data compression. This algorithm is used for data compression. We have already discussed and we have seen how data compression happens. Say you have a message of 20 characters. You have a message of 20 characters which you want to send from one place to another place or one machine to another machine. Then you can either use the standard 8-bit encoding, standard 8-bit encoding, ASCII encoding, where every character or every symbol is represented by 8-bit binary code, Then we modified this 8-bit characters to a 3-bit character. Since we were using only 5 types, of characters. We used 3-bit encoding. So these are all fixed length. These two are fixed length. So we saw that if we used 8-bit encoding, probably this came to 160 bits, or 160 bits were required to send that message of 20 characters, which was sent using 8-bit encoding. Then this required, say, 115 bits. 115 bits of data was required, or size of the message was 115 bits to send 5 different types of characters using fixed length 3-bit encoding. Then we also saw variable length encoding. Where each character required variable length of bits. Some of them required 3 bits, some of them required 2, some of them 4, and so on. So the table that we saw there, it had characters, then it had count, and then it had encoding. So say character A, character B, C, and D. So here we had count. A was repeating 5 times, B was repeating 3, C was repeating 5 times, and so on. So here we use the count of those characters which were appearing in that message. So in today's class, instead of count, we'll be using probability. We will be using probability of characters. So instead of count, we'll be having probability over here. So using this probability, how we can do the encoding and how we can construct a Huffman tree. So we'll be constructing a Huffman tree, and based on this Huffman tree, we'll see what kind of encoding we can get. So this is going to be a variable length encoding. This is not going to be a standard 8-bit encoding. These characters with their probabilities, they are going to have variable length encoding, and this variable length encoding will be deriving it from this Huffman tree. We'll see how to construct a Huffman tree for this Huffman coding algorithm. Right. So in the previous lecture, on the first Huffman coding algorithm or lecture, we have seen the count. We have constructed the tree based on the count of characters. In today's class, we'll be seeing the Huffman tree constructed based on the probability of those characters. All right. Let's see that. Alright, so this is the table what we have. I have the characters, I have the probability. As you can see, instead of the count, here the probability of those characters is written, and here I'll be generating the code and the total number of bits required. Right? So I'm going to calculate the average number of bits, required for per character or per symbol. Average number of bits required per character or per symbol. So this is what I'm going to calculate using Huffman coding by constructing a Huffman tree. Alright, so the first step, I have characters with their respective probabilities. First I need to arrange these probabilities in their increasing order. Alright, so I'm going to choose the two most minimum probabilities out of all these. Alright, so out of all these, which are the most two minimum? I think A and D. So A has 0.11, D has 0.09. So I'm going to choose these two, A and D. Alright, so when you are constructing a tree, make sure that the greater probability is placed on the right hand side and the lesser probability value is placed on the left hand side. Right, so I'm going to place 0.11. So out of these two, this is the greatest, 0.11 and 0.09. So 0.09, since it is less, I'm going to place it at the left hand side, and 0.11 is the greater among the two, that is why I've placed it on the right hand side. So the 0.11, it represents A, 0.09, it represents D. Alright. Next, I need to add them. So what will be the total here? When I add them, when I merge these two values, it will be 0.20. Now these two are done. These two characters are done. Now out of the remaining B, C, E and this 0.20, which are the two minimum? Out of these here? A and D is over. Remaining are B, C and E. They have their corresponding probabilities. And also this addition what we have got out of these two characters. Now among all these four, which are the two most minimum? I have 40, 16 and 24, and this is 20. So 16. So choose this. So 0.16 is less than 0.20. So write it here on the left hand side. So 0.16, which character does it represent? It represents the character C. Add them. When you add them, what will you get? It is, I think, 0.36. You will get 0.36. So B, E and this addition, out of these three, 0.40, 0.24 and 0.36, which is the least? 0.24. So it is less than 0.36. So write it here, 0.24. What will be the addition of these two? The addition of these two will be 0.60. So 0.24, which character does it represent? It represents E. Next, which character is remaining now? B. E is done. B, only this thing is remaining. So 0.60 and 0.40. 0.40 is less than 0.60. So this is 0.60 and 0.40. I don't have space over here, so that is why I have written it here. So add these two. What will you get? 1.00. So the addition always of these probabilities has to come to 1. 1. If you don't get 1 over here, then you've made a mistake somewhere over here. So this is A. This is A. Alright. Next. Now we have constructed the Huffman tree. Now we need to take care of the encoding. So wherever you have these left hand side edges, you have to mark them with 0. So 0, this is 0, 0, 0. Wherever you have right hand side edges, mark them with 1. 1, 1, 1, 1. This is the root node. This is the root node here. Since I had no place over there, I have drawn it here. This is the root node. Alright. So I have covered all the characters A, D, C, E and sorry 0.40 is B. 0.40 is B. So this is done. Now I need to find the encoding of A. So if I have to reach this character A from the root node, which path do I have to take? 1, 1, 1, 1. So it is 1, 1, 1, 1. It is 1, 1, 1, 1. Just trace it from the root node if I have to reach A. So it is 1, 1, 1, 1. Next one is B. So B, where is the character B present over here? Here. So it is 0. It is only 1. Only one character. See, this is the root node. I am reaching B, so only 0. Next character is C. So if I have to reach C, how do I reach? 1, 1, 0. Root node 1, then 1 and then 0. So C will be represented as 1, 1, 0. B is represented as 0 with only 1 bit. Next, the character D. If I have to reach D, then it is going to be 1, 1, 1, 0. 1, 1, 1, 0. E. What is E? How do I reach E? So it is 1 and 0. First go to 1 and from here 0. So it is 1, 0. As you can see over here, we have not used the standard 8-bit encoding for sending or compressing the message. We have used variable length. A uses 4 bits, B uses only 1 bit, C uses 3, D uses 4 and E uses 2. Now I am going to calculate the total. What is the total? 4 bits, 1 bit, 3 bits, 4 bits and 2 bits. 4 bits and 2 bits. Yes. Now I need to calculate the total number of bits required or average number of bits required in order to send these characters. So how do I do it? So probability multiplied by the number of bits, probability of this character, I means the character, probability of this character multiplied by the number of bits. So summation of I equals to 1 to n. So when I calculate this, I need to also add, because I need to calculate the sum of all these characters. So it is summation I equals to 1 to n. 1 to n means 1 to 5. I have 5 characters, so 1, 2, 3, 4, 5. What am I doing? Probability of I. So probability of A multiplied by total number of bits. Probability of B multiplied by total number of bits. Probability of C multiplied by total number of bits. So I need to add all these things. So it's going to be like this. So 0.11 multiplied by 4. This is for the character A. Then plus 0.40 multiplied by 1 plus 0.16 multiplied by 3 plus 0.09 multiplied by 4 plus 0.24 multiplied by 2 multiplied by 2. So this total, what does it come down to? It comes down to 2.16. So the total of this is 2.16. So this is 2.16 bits required per character or per symbol, per character or per symbol. See, A requires 4 bits, B requires 1 bit, C requires 3, D requires 4, E requires 2. But what is the average number of bits required? The average number of bits required are 2.16 bits. So this is how compression has taken place. If this was standard 8-bit compression with the frequency, probably we would have got a bigger value, right? So this is a minimization problem. I am compressing data, I am compressing the size of the data which is being sent. So this is a minimization problem. So 2.16 bits per character on an average is required to send these number of characters over a network. So this was another version of Huffman coding. In the previous lecture we had seen the characters with their count. We first used standard 8-bit encoding, then we used 3-bit fixed length encoding, and also we did variable length encoding by constructing a Huffman tree over here, or minimal merge pattern tree. And so the same thing we have done here, but instead of counts over here I have taken probabilities. So this is exactly how you do or how you solve Huffman coding. You will be given this character and probability, and you have to calculate the average number of bits in this fashion, in this manner. Alright, so this was another version of Huffman coding algorithm, and this was the last of your unit 4. Thank you very much.